Okay, welcome to today's lecture. This is definitely the first time I've said all of this, not the second time, because I always remember to start the recording at the beginning. So, on one of the worksheets, there were a lot, it was the copper cycle worksheet, where you took copper, well, my dad took copper, uh, Dr. Kawagoa took copper, and he dissolved it in acid. And then there were a bunch of other steps in there that took it from the acid, and then you heat it up and it becomes the oxide, and then you dissolve it again, and then you added copper to or zinc to it to get back your copper metal, and you weighed out or measured what your yield was from that. How much copper did we lose along the way? There were a lot of reactions in there where you had to predict the products, and there were a few people who seemed to really struggle with these double replacement reactions in particular, and also just sort of predicting the products of reactions. These are actually from what I think it's homework 8. I was just looking at it. Chapter 8 homework. And these ones will actually produce solids. So it's saying there's a test on Friday, the final test. It's not technically a final because it's worth the same as the other exams. But there will definitely be a question on there that's asking you to predict the products of a reaction, and you should make sure that you check to see if those products, any of those products, is a solid. Excuse me. So these are actually all, well, some of these could be precipitation reactions, some of them could not. You can go back later and check and test your solubility knowledge. Like I said, this is from that homework 8, or chapter 8 homework. But we're just going to go through and we're going to predict the products of these and try and take it maybe step by step. There's about 8 of these. And then somebody who's here live will remind me at the end just one more note about the final. Or the final exam, not the final. Okay, so our first reaction here, we have potassium iodide with barium sulfate, or sulfide, barium sulfide. Oh, that was something I wanted to note. On that lab too, it told you what the reactants were if you read the sort of description above each of those reactions. Yeah, so anyway, so we have potassium iodide and we have barium sulfide, IDE, sulfide. And so what we're going to do first, and this is the way that I do these, is I take my cations. So we always have our cation first. And we take our cations and we move those over to the product side. And you want to write them, you might want to write them with their charge. And don't write their charge like right next to them because you're not going to need that in their formulas for the resulting products. But you can write the charge above it. So we got potassium, which has a positive charge, right? We know that because it's a 1A compound. So we're going to have potassium, and then we're going to have something with it, plus barium. Now barium is a 2A compound, right, from group 2A, and so it's going to have a 2 plus charge. And then we're going to have something with barium. And actually, to sort of improve clarity here, let me do these in different colors. So this was iodide, and this was sulfide. And so what we're going to do now is we're going to swap the anions. So we get potassium sulfide, and we're going to get barium iodide. Now what you need to do at this stage, and we should write these charges down too. So iodide has a -1 charge. And then our sulfide is actually going to have a 2- charge. So it's at this point, so we talk about a lot where with these, when we have molecules, right, you don't change the subscripts. But when you're predicting products, you need to balance your charges, and so you need to change your subscripts. So for potassium then, because sulfur or sulfide here has a -2 charge or a 2- charge, potassium only has a +1 charge, so we need 2 potassiums to balance that charge. And then if we go over to barium iodide, we'll see that barium has a 2 plus charge, iodide has a -1 charge, so we need 2 iodides to balance that charge. And it's at this point where you come back in and say, okay, well now I need to balance the reaction, right? Because that's the kind of question that I'll ask. Mostly to avoid having to write out each of the possible. Typing these reactions into Canvas is just an absolute pain. So this way I can make you write these out, and I don't have to write out so many of them. Because I get to write 4 for each problem. Okay, so well, let's just balance this really quick. So we have 2 potassiums. And so we'll just come over here and we'll say, okay, we put 2 in front of that. Now we have 2 potassiums. That means we have 2 iodides on the left side. And if we go over to the right side, we have 2 iodides. And then we can check that sulfur and barium, we have 1 on each side, so it's balanced. Okay, so those are sort of the steps that you should take. And again, we'll do this next one. We're just going to crank through these. Really get some reps for practice. So again, we take our cations first, potassium. All right, so potassium, again, plus charge. It's going to have something here, plus. Barium again, it's going to be a 2 plus. And right, you might be saying to yourself at this point, like, oh, well, some of these are going to be solids. But again, we're just ignoring the precipitation part of this for now. So now that we've got our 2 cations written down, we're going to swap the anions. So bromine was with barium before. So bromine, I should probably indicate like this. Bromine is with barium here, but bromine is going to be with potassium on the right side. I'll just keep using black because that's what I wrote them all out in. And so bromine has a minus charge, right? It's a halogen, 7A. And then we're going to take our sulfate. So sulfate here is with potassium. And we're going to take it and we're going to move it over with barium on the right side. And sulfate has a 2 minus charge. Now when we take a look at these, again, we need to make sure that our charges are balanced. And we always are going to have a positive charge with a negative charge. I guess the one exception would be if we do a combustion reaction. A combustion reaction will look something like CH4 plus O2. Most of the time, if you have something with carbon, especially written with an O2, that's going to be a combustion reaction. And those products will be CO2 plus H2O. So that's one of the exceptions. The other ones would be gas evolution reactions. But let's keep going here. So to balance this then, we would just take, and really when I do these balancing problems, almost all of the time you can just sort of pick one of these elements that's not balanced, or one of these polyatomic ions that's not balanced. So if we take a look, okay, so let's do potassium. Let's just start on the left side. Potassium's not balanced. So we have 2 potassiums on the left and 1 on the right. So I'll put a 2 here. And actually, so so I did potassium, right? So potassium's balanced, but this 2 also changes bromine. So I'm going to look at bromine now, and I say we have 2 bromines. Oh, we have 2 bromines on the left side too, right? Because it's got this subscript. So then we can look at barium on the left side, and then we have barium is balanced. And then we can look at sulfate, and we can see that sulfate is balanced. Right? Not too hard. All right, so again, we have sodium and we have mercury, right? Our cations are written first. Because what I saw on some of these worksheets was that people were writing sodium and then mercury together plus, I think it's acetate. Sorry. H3O2 and chlorine. And this is now a plus charge and a plus charge and a minus charge and a minus charge. And opposite charges are going to repel each other, right? So you're not going to have opposite charges combining. And that's sort of a way that you can check to make sure that you've done this correctly. So that's not the way we're going to do this. We're going to do sodium. Again, that's our first cation. We're going to have that combined with something. And then mercury is going to be our second cation. Now, sodium is easy. It's a 1A compound, so it's a +1 charge. Mercury is a little more difficult, and what you have to do for mercury, and at least in this case, you have to know that acetate has a -1 charge. So if we just focus in, let's just focus this in here on mercury acetate. If we know that acetate has a -1 charge, each acetate has a -1 charge, and we have 2 acetates, that means that this overall charge, all right, so I'll write it like this. It's a -1 multiplied by 2. It's going to be equal to a -2 charge. So we know that the charge on mercury, the overall charge on mercury, has to be plus 2 to cancel out this minus 2. And because we have two mercuries, we know that the charge on a single mercury is going to be plus 1, because there are two of them, and that will equal positive 2 charge. Okay, so now we figured out the charge on mercury. We can say that this is a positive charge, right? It's a plus 1. And now we swap our anions. So sodium is going to get a C2H3O2, right, or acetate. And mercury is going to get chlorine. We've just taken those and swapped them. So then we can actually look at the charges here, and we'll see that the charges of our products are balanced. This one, if you go and check the book, mercury 2, again, this is one of those, there's so many, I'll say there are a few exceptions in chemistry, and that can make things a lot confusing, right? But the vast majority of problems are not going to be like that. For the sake of this, let's just say that it's mercury by itself. And now we just need to balance. So we'll say that, let's just pick something that's not balanced. Let's pick mercury, right? We have H2, or Hg2, mercury, two mercuries. And so we need 2 on the right. Oops, that's your eraser. So that means we have 2 chlorines. And so we're going to go back over here and say, okay, we need 2 chlorines on the left, which gives us 2 sodiums. And then we need 2 sodiums on the right. And I don't know if you're picking up on the way that I do these. When I start with one of these compounds, or one of these elements really, and I move and I change the coefficient, you can't see my finger pointing. So if I change it, right, mercury has 2, so we add a coefficient for mercury. Well, that's going to change chlorine. So then I say, okay, now that I've changed chlorine, we have 2 chlorines. Then I go over here and I say, oh, okay, we need to balance chlorine. We need 2 of those. So I put a coefficient of 2 here, but that also changes sodium. So I say, okay, well, now I've got 2 sodiums. So I go back over to the right side, and we saw that, oh, we needed to add a 2 so that we could have 2 sodiums. But that 2 also changes acetate. So we say, okay, well, now we've got 2 acetates, and we look at the left side, and we've actually got 2 acetates already, so we're balanced. And so by moving from element to element like that, you can fairly easily balance, especially these double replacement reactions. It's a little bit, just a little bit more complicated if you have something like a combustion, because then you have elements that are by themselves. So those are dead ends. So you want to end there and do that one last. Anyways, moving on. So again, we got sodium, plus charge. And we're going to have that with one of our anions, right? The other anion, really. And we've got lead. And again, we need to determine the charge on lead. And so this is where knowing your polyatomic anions is very helpful. So you don't have to look up that nitrate is a 1 minus charge. Because we have 2 of those, the charge on lead is going to be a 2 plus. So we do a 2 plus over here. And then we can have, now that we've got our charges and we've got our anion, or cations in place, I should say, now we can swap our anions. So we'll take this anion, right, acetate, with the sodium, and we're going to move that over, and because it was with sodium before, it's going to be with lead now, C2H3O2. We know that has a minus 1 charge. And then we're going to take the nitrate, which was with lead before, this is the nitrate, and we're going to add that to the sodium, NO3. And we know that has a minus charge. And now we just look to check where our charges aren't balanced. So sodium and nitrate, that's a plus 1 and a minus 1. So those are balanced. Lead has a plus 2 or 2 plus charge, and acetate has a plus 1 charge. So we just add a subscript to the acetate to balance those charges. Yeah, simple as that. Not so bad. Okay. Keep plugging, keep chugging. Na right? So we got sodium, sodium. That's going to be a plus charge with something else there. Iron. And again, we need to determine the charge on iron because the only non-main group, right? The main group is 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. The only main group elements that we know the charges for all the time, because they only have a single charge. Let's go to the periodic table here. I wish I could pointer on this, but I can't. We have aluminum, right, which is over in 3A. Aluminum, zinc, and silver. Gallium, and I believe actually cadmium and indium might also have single charges. You know what? Let me just double check there. I think I looked this up, and cadmium forms, yeah, a +2 oxidation state, and indium, I'll bet, is a +3. Mm, it looks like it's a +3. So you have, and gallium is a +3. So gallium, indium, cadmium, silver, and zinc, those all have single charges, and those are the only transition metals that we have that have single charges. Oh, and scandium. Scandium forms a single charge, +2. Okay, back to this though. So be aware of those. Bromine, again, 7A, so it's a -1. And this is actually, I want to make a point here too. When I ask for the oxidation state on bromine, I'm asking for the oxidation state of a single bromine, not on all the bromines together. I just want to know the oxidation state of a single bromine. I've asked that question on the last 2 tests now. That question will be on the 4th test. So be aware. Be aware. Not beware, be aware. Okay, but since we have 3 bromines, that's a 3- charge. And our iron then is going to be a 3+ charge, because those charges balance. So now we're going to take these and we're going to swap our anions. So we're going to take the hydroxide, which is on sodium. I'm going to talk a lot about hydroxide today, and put it on the iron, and we're going to take the bromine and we're going to put that on the sodium. So once we've got those placed, we can check our charges. Bromine is a -1. Again, polyatomic anion, hydroxide is a -1 charge. How much time have I taken on this? Okay, we don't want to go too long on this. But because we have a single minus charge for hydroxide and a 3+ charge for iron, we're then going to add a 3, and make sure you add the brackets or parentheses to indicate that we're multiplying this entire group by 3. And then we can balance. So let's just start with the hydroxide since we're there. We need 3 of those on the left. So we now have 3 hydroxides, and we have 3 sodiums. So we're going to take our sodiums, and we're going to say there's a 3 over here. That gives us 3 sodiums and 3 sodiums, right? 3 and 3. And then we have bromine. Now we have 3 bromines. And on the left side, we have 3 bromines. So we're perfectly balanced there, just as Thanos wanted. So let's move on to the next one. Hopefully this is, helpful for someone out there. One of the things that's a struggle for me, I think, is that when I see these things on exams or on labs, I know that there's only a few people who show up for the live lectures and sit through all of my gabbing, but hopefully the rest of you are watching the lectures. So we've taken our cations here and we've moved them, right? And we've just moved them over. We've kept them in the same relative order. Barium first, silver second, and then we're going to add the anions to them. Barium we know is a 2+ charge. Silver we just talked about is a +1 charge. 1+. And now we take our cations, and we swap those. So we have silver chloride, and we have barium nitrate. Nitrate has a -1. Chlorine has a, I keep saying -1, it's technically 1-. Technically 1 minus. Okay, so those both have 1 minus charges. Can write those, I suppose. So now we just need to look and see where we need to balance, and we'll see that nitrate needs to be balanced because barium has a 2 plus, nitrate has a 1 minus, so those balance that way. And now we can see that we just need to balance out the rest of this, and so we'll say nitrate has 2 on the right side, nitrate has 2 here, there's 1 here, we add a 2 coefficient to balance those out. Then we see that we've got silver. So we need to go to the right side. We need to balance silver. And I didn't leave much room here, but we're going to add a 2. Now that silver is balanced, then we can see that we have 2 chlorines now, right? 2 times the coefficient. But we have 2 chlorines already on the left. For barium, we already have 1 barium on each side. All right. Again, it's the same steps every time, especially for these double replacement reactions. We're just going to do Na. And this works too for a single replacement reaction. You just have 1 cation. So you move the 1 cation over and you swap the anions, you're good to go. So we'll do sodium, which has a 1 plus cobalt here. And we're going to have something else with that. Cobalt, again, we need to determine the charge on cobalt. But since it's bound to, over here, a chlorine, the chlorine we know has a 1 minus charge, or a 1 minus oxidation state, times 2 means that cobalt is going to have a 2 plus charge. So then we just swap our coefficients here, and we have CO3, and we have Cl, sorry, our coefficients. I meant swap our anions. We write in their charges, and actually what we find here is that the charges are already balanced, right? So cobalt has a 2 plus, which we determined from the reactant, cobalt chloride, and then carbonate has a 2 minus charge, sodium has a plus 1 plus, and chlorine has a 1 minus. So now we just need to balance our coefficients. Since we didn't add any subscripts on the right, I'm just going to start on the left, and we're going to do sodium. Start with sodium. There's 2 sodiums here, and there's 1 sodium here, so we balance him, or them. I'm not going to assume sodium's gender. So now we have 2 chlorines, and actually we have 2 chlorines on the left side. And if we look at cobalt, right, single cobalt, carbonate, carbonate. We're good to go. All right, one last quick problem. Potassium sulfide. So we're going to do potassium, right? That's going to be bound to something else. Barium, that's going to be bound to something else. This is a plus charge. Barium we know has a 2 plus charge. And then sulfur. All right, so we took the sulfur from the potassium, put it on the barium. Now we're going to take the chlorine from the barium, the chloride from the barium, and add it to the potassium. That's a minus charge, and this is a 2 minus charge for sulfur because it's a 6A compound, main group metal, or main group nonmetal. And now we just balance our reaction equation. So once you've gotten past this point and you've balanced the charges of your products, you're not going to be changing any coefficients anymore. That's where you stop changing the coefficients. So now we're going to look and we see we have two potassiums. Ooh, I could do the whole laser tail. What does that do? Potassiums. Oh, I like that. All right, so we're going to do, and then we're going to match that to this one over here. So we're going to just put 2 of those, which gives us 2 chlorines, which we match to the 2 chlorines here. So then those are balanced. And we can look at barium next with this barium and see that those are balanced. Wait a second, why is it K2S3? I might have written that down wrong. Let me check real quick. Where is the textbook? K2. Oh, now I have to find it. I think I wrote that down wrong because the charges don't balance. It's K2 and barium chloride. It's farther up here. Okay, here we go. Here we go. K2S3 and barium chloride. I guess this is one where you have to look at the oxidation states. Um, I'm sorry, I actually don't know exactly what to do with this one because potassium should have a plus charge and sulfur should have a 2 minus charge. Um, so I suppose it's possible that because what this is suggesting is that potassium has a 3 plus charge and that sulfur has a 2 minus charge, which is why they would balance this way for a compound. Let's just, I'm just going to rewrite this one real quick. K2S. I'm going to have to look into that and see why that was the case. So we have K2S, so it's still 2 potassiums. Now we have a single sulfur. We have our 2 chlorines. Right, so this balances here because of this. And then we have sulfur with a single sulfur. Weird. That might be a typo. Good thing it's one of the even problems. Oh, this was chapter 7. Chemical reactions was chapter 7. Okay. So that does it for those. Hopefully those are helpful for somebody. That note, I didn't forget. The note about the test was that this exam 4 score, will replace, if it's higher than one of your other scores or your lowest score, it'll replace your lowest exam score. So if you get an 80 on this and you had a 70 on a previous exam, then that 80 will replace the 70. And so give you a little boost because this is in all but name, really, in all but name, it's a final because it is cumulative, right? So I'm going to have a little bit of everything. It will be mostly focused on these last 4 chapters. So starting with solutions that we talked about yesterday, acid bases today, and then we're going to do a little bit of radioactivity. I think acid bases and solutions are going to be the real focus of this exam. Okay. I'm going to set, because I remembered this time, I'm going to set a 30-minute timer on my watch here, and then we'll take a break at 11. Okay, so acids and bases. So yesterday we talked about solutions. Acids and bases are a subset of solutions, really. They sort of fall under the same category. I did recently, it's kind of funny, I recently saw a TikTok, yes, I'm on TikTok, recently saw a TikTok of Hank Green talking about how you can taste protons, which is funny because that's what we're talking about today. Acids are what make things sour. And acids primarily produce protons. And so what your body is tasting, what your tongue is detecting, are those protons. So we can taste protons and they are sour. So things like citric acid, found in lemons and limes, acetic acid, which is present in vinegar. It's a slightly different kind of sour. Tartaric acid, which is one of the acids used to coach Sour Patch Kids. If you have a sour warhead, those are acids. The acids combine with saliva in your mouth, and they produce protons, or a hydrogen plus ion, right? Because hydrogen only has 1 electron, so if it loses that electron, it's just a proton. So acids combine with the saliva to produce protons, or hydrogen ions. These hydrogen ions then react with the protein molecules on your tongue and send an electrical signal, or nerve impulse, to your brain that you experience as sour taste. Properties, an example. So acids have a sour taste. They dissolve many metals, and they turn blue litmus paper red, which is sort of just, if we were in the lab, we would do this, and you could see that, you can test and see if something is an acid. Litmus paper actually has a cool story. I believe it was derived from a lichen. You can look that up. We use acids a lot. Maybe not always in, our own household, but they can be used for hydrochloric acid can be used for metal cleaning, food preparation, or refining, and it's a main component of stomach acid. So you do use hydrochloric acid every day, whether you know it or not. Sulfuric acid and nitric acids are primarily used for fertilizer and explosive manufacturing, which does include things like fireworks, dyes and glue production, automobile batteries. Um, Sulfuric acid is the primary acid in car batteries. There's also things like acetic acid, which you can use for plastic and rubber manufacturing or food preservation, which is the active component in vinegar. So when you pickle something, right, pickling is you soak it in vinegar and salt for a long time. That's the food preservation. You're using acetic acid there. Carbonic acid we find in our carbonated beverages. We talked about that yesterday and how um, really when you're dissolving that carbon dioxide in water, it's forming carbonic acid. Hydrofluoric acid is actually there are chemicals to be afraid of, and there are chemicals not to be afraid of. Hydrofluoric acid is a chemical to be afraid of. Um, it will ruin your last few remaining days. Yeah, if you encounter it. Properties of bases. Bases have a bitter taste. It's not all bitter things, but have a bitter taste. They have a slippery feel because they react with the oils on your fingers to make soap, basically. Huh, basically. Pun unintended. Bases turn red litmus paper blue. We got two different types of litmus paper. All of these consumer products contain bases. A lot of these are, um, I have never heard of Fantastic. That was one. I think I've heard of Comet. I was surprised to see tonic water in this list, actually. Bases feel slippery because they react with oils, right, like I just said, to form soap like substances. Bases are much less common in foods. And alkaloids are a sort of class of bases, and they are found in plants like hemlock, which are often poisonous, and their bitter taste warns us against eating them. Coffee, actually, overall is acidic, but caffeine is basic, and so that's what makes it bitter. Deliciously bitter. Um, some common bases here we have things like sodium hydroxide, which is petroleum processing, soap and plastic manufacturing. I think sodium hydroxide is also the main component of drain cleaner. Potassium hydroxide, cotton processing, electroplating, and soap production. I can't remember which one it is. It's potassium hydroxide or sodium hydroxide that you use for, or it's lye. And so you can use it for canning peaches and fruit. Sodium bicarbonate is a antacid ingredient of baking soda and source of CO2. So that's what's in. Actually, is that the? I think it's Alka-Seltzer, but it's also Tums. Sodium bicarbonate neutralizes stomach acid, and we have ammonia, which is a detergent, fertilizer, also used in explosive manufacturing and synthetic fiber production. Um, I believe it was ammonia. No, it was a different fertilizer. It was like ammonium nitrate that was being stored. Where was that? Beirut? Can't remember. That massive explosion from a while back. It might have been a year ago now. Improperly stored. The Arrhenius definition of acids is that an acid produces H plus, right? Hydronium ion, or well, no, hydronium is the other thing. It produces H plus ions in aqueous solution. So things like hydrochloric acid, it's a covalent compound which does not contain ions, but when you add it to water, it ionizes and that splits apart. Right? We talked about net ionic equations and electrolytes. Hydrochloric acid is one of those, and so when you add it to water, it ionizes and splits apart, and you get these positive hydrogen ions floating around, or sour protons, and then we get chlorine ions or chloride ions. Um, so hydrochloric acid is an Arrhenius acid. No. These H plus ions are highly reactive, and actually in an aqueous solution they bond to water, according to this reaction here, and they form what's called hydronium. So this is hydronium. It was water with an extra hydrogen. In water, the H plus ions always associate with water molecules, so they're never actually found alone. They're always hanging out on a water. And we do often use these interchangeably to refer to a hydronium ion. When you're writing the molecular formula for an acid, we usually write the ionizable hydrogen first. That's why HCl, acetic acid is one of them. This is formic acid. So we put this hydrolyzable or ionizable hydrogen first. The structural formula shows how the atoms are bonded together. All right, we got our structural formula. And the molecular formula indicates the number of each type of atom. So this would be like a molecular formula. So you can see that this ionizable hydrogen is actually over here attached to an oxygen, and this is actually called a carboxylic acid. Little OChem term for you. Our bases, on the other hand, so we talked about our acids and the Arrhenius definition. Bases produce OH ions, hydroxide ions, in aqueous solution. So sodium hydroxide is an Arrhenius base because it dissociates into sodium and hydroxide ions in the solution. Oh, there was a chat thing here. Oh, yeah. Okay, so molecular compounds containing an OH group such as methanol do not dissociate and do not act as bases. I was trying to come up with a way that because I know this intuitively, but I've also been doing chemistry for 10 years now. So part of the reason that this is that this is a molecular compound. It's not an ion, or it's not an ionic compound. Sodium hydroxide is ionic because we have a cation, a metal cation, bound to one of our polyatomic anions. Yeah, cation bound to an anion. But when we have this, we have carbon bound to an oxygen, which is a polar covalent bond, and not an ionic bond. We're not going to use the Arrhenius definition too much. Under the Arrhenius definition, acids and bases naturally combine to form water, neutralizing each other in the process. So if we have an H plus ion and we have a hydroxide, you can see how those pretty easily form together to make water. But what the Arrhenius definition doesn't explain is why some substances act as bases even though they do not contain hydroxide. Specifically, that would be something like NH3+. It's one of those. Sorry. I like this is fun. It just disappears. Okay, so the Arrhenius definition does not apply to non-aqueous solvents. So you can't talk about acids and bases in something like hexane or octane or something dissolved in oils, because we can't have hydrogen and we can't have hydroxide in the same way. So we have also the Bronsted-Lowry definition of an acid and a base, and this is a better definition. It's more broad. The Bronsted-Lowry definition of an acid is that an acid is a proton donor. So our proton, again, I said, or hydrogen, right? Hydrogen only has one electron. If it loses that one electron to become a positive, it's only a proton. We're not talking about deuterium or tritium here, which are the isotopes of hydrogen. Just hydrogen as a single proton and a single electron. So losing that, we just have a proton. So then a base is a proton acceptor. So acids donate protons, bases accept protons, and this definition applies to a wider range of acid-base phenomenon. And it focuses on the transfer of hydrogen ions or protons in an acid-base reaction. So HCl is a Bronsted-Lowry acid because in solution it donates a proton to water. So you have HCl and water, right? And then we have this extra proton which came from the chloride or hydrochloric acid to form this free chloride. So this definition more clearly accounts for what happens to the hydrogen ion from an acid. It's transferred from the acid to the water. And actually here then, so water, or I guess water up here is the, I'm just going to abbreviate this as Bl base because it accepts that proton. And this is going to be our Bronsted-Lowry acid. The Bronsted-Lowry definition works well with bases also like NH3, which I mentioned briefly before, which does not contain a hydroxide ion, but still produces hydroxide ions in solution. And this is because our NH3 accepts one of these protons to become NH4. And that produces then a hydroxide in the solution. So just to go through these again, this is our Bl base. And now you'll see that water, and we'll get to this, but water is a Bronsted-Lowry acid here because it's donating a proton. So water can be both. So acids and bases, proton donors, proton acceptors, always occur together. You have to have both because the proton has to go somewhere because the acid has to donate it to something. So this is where we see that we have this new fancy word called amphoteric. An amphoteric substance, such as water is just one, can act as an acid or a base, so it can accept a proton or it can donate a proton. When the equation representing Bronsted-Lowry acid base behavior of ammonia is observed, ammonium is reversed, the ammonia, gosh, I always get these two mixed up. The charged one is ammonium, the uncharged is ammonia. So if we reverse this, then our ammonium is now our proton donor, and our proton acceptor is this hydroxide to become water. In this sense, so this is a little bit different than something being amphoteric, because water can either accept a proton to become H3O, or it can lose a proton to become OH minus, and that's what makes it amphoteric. The difference here is that we have NH3 can't lose another proton to become NH2 plus. This doesn't happen. It can gain one, and so what you get is this just, you get two things sort of that can happen, but it depends on which one we have. So then this would be NH4 plus, or I guess this would have been minus. Anyway, so we have NH4 plus, NH3. This is a conjugate acid-base pair. So you could also say for water, just one of these, this is an acid-base pair, this is, oh, a little too far there. This is an acid-base pair. So water has two different acid-base pairs. It can go in one direction or the other. Ammonia and ammonium can only go in one direction depending on which one you have. So again, any two substances related to each other by the transfer of a proton can be considered a conjugate acid-base pair. So if we have HCl, the conjugate acid-base pair would be Cl minus. If we had NaOH, well, I guess that's really well, this would really be OH minus, right? The conjugate acid-base pair would be H2O. So I can think of another one off the top of my head. Trying to think of something different, right? So we could do, HNO3. So that's the acid, because it's a donor. Its conjugate base pair then would be NO3 minus, which would be the base. This would also go for polyproducts. So if we had H2SO4, then so it's the acid, so then its base would be HSO4 minus. But that's getting into polyprotic acids, and we'll get there. So the base accepts a proton and becomes the conjugate acid, and an acid donates a proton and becomes the conjugate base. The important thing to note here, and especially in terms of test questions, is that the acid is going to be one of the reactants, the conjugate base is going to be one of the products. The base is going to be one of the reactants, the conjugate acid is going to be one of the products. So if I ask you, if I give you this reaction here, and I say, what is the conjugate acid in this reaction? That's a little too vague. I don't know if I'd ask it that way, but if I asked you what is the conjugate acid in this reaction, NH4 plus would be the conjugate acid, not H2O. H2O would just be the acid. So let's look at each of these reactions, and let's identify the Bronsted-Lowry acid, Bronsted-Lowry base, and then we'll identify the conjugate acid and the conjugate base. So, actually, let's just do this. Okay, what is our C5H5N? Is that acid or base? You can just put it in the chat. C5H5N. Bronsted-Lowry base. Wait a second, see if anybody else is going to reply. If anybody wants to contest. Nope. Yep, that's correct, because, right, it's accepting our proton, so we got our Bl base, which then would make our water, or Bl acid. And then on the other side, right, OH minus would be our conjugate base. And then this would be our C5H5NH plus, would be our conjugate acid. This is the kind of question that I would ask, right? I would say, okay, given this reaction, is HNO3 conjugate acid, conjugate base, acid, or base, right? So you'd get all four options. So for HNO3, is that our Bronsted-Lowry base, or is that our Bronsted-Lowry acid? Or is it a conjugate base? Yeah, Bronsted-Lowry acid. Which makes water here Bronsted-Lowry base, right? Again, it's amphoteric. And then nitrate would be our conjugate base. And hydronium, this is hydronium, would be our conjugate acid. Text or something? No. Okay. Just Readley College sending out lots of emails. So our acid-base reactions generally form water and a salt, an ionic compound. The net ionic equation for many of these neutralization reactions is just going to be H plus hydroxide is water, makes water. That's usually the result of a neutralization reaction, if you're to write out the net ionic equation. Ammonia might be one of those cases where it's not that. The reaction of acids with carbonates or bicarbonates containing CO3 2- or HCO3- produces water, gaseous carbon dioxide, and a salt. So this is where we talked about composition reactions. But what we didn't talk about is that when you have carbonates, that those are gas evolution reactions, and they're also acid-base reactions. And right, so it's also called a gas evolution. because again, you could write out the net ionic equation for this and see that NaHCO3 would split into Na plus H plus CO3 2 minus. And then our HCl is going to be H plus Cl minus. And so ultimately what you're going to get here, I guess you get the carbon dioxide, but your Na and your Cl are going to cancel out in your net ionic equation. And so you'll get basically 2H plus CO3 2 minus is H2O plus CO2. And that would be your net ionic equation. Let's write a molecular equation for the reaction that occurs between H3PO4, so phosphoric acid, and aqueous sodium hydroxide. So we're going to have, again, there's this hint, H3PO4. So I mentioned briefly polyprotic acids. H3PO4 is one of those. So we're going to write out NaOH plus H3PO4. So we're going to have a neutralization reaction because we have an acid and we have a base. And H3PO4 is going to be a Bronsted-Lowry acid. It's going to be our Bronsted-Lowry base. And so what we're going to end up with is NaPO4 plus H2O. But we're going to need 3 NaOHs for each of these 3. So we need 3 of these hydroxides for all 3 of these protons. And then so each of those oxygens is actually going to be, and this is where it very much helps to know your polyatomic anions, because we know that these oxygens, we don't need to balance those except as a part of PO4. So those oxygens are all the oxygens that become water. So we're actually going to have 3 of these. Oops. And then we're going to have, we need to balance those. Yeah. Wait, I feel like something feels off. Because then we're going to need 3 of these.
2 of those.
Oh, there's hydrogens here too. Sorry, what did you say?
Is that if you were going to put the 3 H3PO4, it would only be 2, but there's the 3 extra hydrogens over there. So it still balances out to 6 total without the 3 there. It balances, you're right.
It balances?
Without the 3 in front of the H3PO4, it balances because you have 3 hydrogens from the 3 NaOH and 3 from H3PO4.
But then we have 3. We need the 3 hydroxides. So this has to be 3. But then I have to have 3 sodiums, right? Um, Oh, wow. I didn't balance this. Cool. Okay. Right, because NaPO4 or PO4 is going to be a 3 minus, so we need 3 sodiums to balance that charge. Okay. Right, so that should be balanced now because we have the 3, we have these 3, and then these 3, so that's 6, which balances with this. We have our 3 oxygens, which balance there. Um, PO4 is balanced, sodium is balanced. Okay, right, so that's why it's important to balance those charges on the. Again, this is sort of like a double displacement reaction, which I just did 8 of, and I didn't even follow my own steps to balance those charges. So if you start end up, because I was going to end up in a loop if I didn't balance that, because I needed to put 3 here, so that was going to give me 3 of these, which would give me 3 of these, which would then mean I have 9 hydrogens. And then I'd balance the hydrogens, which means I'd increase the oxygens, which I'd increase the oxygens here, which would increase the number of sodiums, which I would then increase here. And so you can see how this would start to loop, and you keep going back and forth and back and forth. That's a pretty sure sign that you have not balanced just the molecules correctly. Okay, so acids dissolve many metals. Actually, this timer's about to go off, so we're gonna take a break there. I'm gonna drink this entire glass of water and then another one, and we'll meet back in 5 minutes at 11:06. Alrighty. Let's get back into this. Set another timer here. Let's go. So acids dissolve many metals. And these mostly react to form hydrogen gas and then a metal salt. So we have something like HCl with magnesium to form magnesium chloride, zinc and sulfuric acid to form zinc sulfate, and HCl, hydrochloric acid, and iron chloride. There are some metals that do not react readily with acids, however. Acids react with metals in a way that causes metals to go into solutions. They dissolve. The reaction between an acid and a metal usually produces hydrogen gas, which is we did the zinc reaction to form hydrogen gas. I believe that was HCl. And a dissolved salt containing the metal ion. Acids react with metal oxides to produce water and a dissolved salt. This though, they react with metals to form hydrogen gas, or they react with oxides to form dissolved salts. So the difference being that it's a metal oxide instead of a salt or a pure metal. Mochi's crying again. So let's write a reaction equation for this reaction. We're going to react hydrochloric acid with strontium metal. So make this a little more permanent. HCl plus strontium, solid, right? Aqueous. We're going to form hydrogen gas plus SrCl, right? And we need to balance these. So strontium has a 2 plus charge. It would be Cl2. Just like that. Now if we react hydroiodic acid, Hi, aqueous, right? So then strontium chloride would be aqueous as well. Plus barium oxide. So barium's a 2 plus, oxygen's a 2 minus. That's going to form H2O plus barium iodide. And so barium has a 2 plus, iodine is a 7A, right? Main group, non-metal. So it has a -1 charge. Barium and oxygen is a 6A, so it's a -2 minus charge. Barium's a 2 plus. And then we just have to balance this. We just place a 2 there. We'll see that we now have 2 hydrogens. And we also have 2 iodines, a single barium, and a single oxygen. Hold on, Mochi locked himself in the bathroom. Okay, sorry. Mochi loves acids. Mochi is just so into chemistry. He's just the perfect cat for a chemist. Okay. The most important base reactions are neutralization reactions, which we already covered. But there's another kind, or the only other kind of base reaction, is the reaction of sodium hydroxide with aluminum and water. And aluminum is one of the few metals that dissolves in a base. And so that's that reaction here. Notice that this is not exactly straightforward. But you can see you have the hydroxide, the sodium, and aluminum. So you form this sodium aluminum hydroxide compound. So we can apply, right? We talked about solution stoichiometry, and we can apply that to a common laboratory procedure called titration. That's what lab 11 is. In a titration, a substance in a solution of known concentration is reacted with another substance in a solution of unknown concentration. The net ionic equation for the reaction between hydrochloric acid and sodium hydroxide is, as we mentioned before, just a proton combining with... Mochi! Stop it! Here, come here. Come here. So again, it's just this simple hydrogen plus a hydroxide forms water. Stop crying. I'm just gonna hold it for a bit while we lecture. Okay, so right, it's this simple net ionic equation that we talked about before, so that those chlorine and the sodium are going to cancel out because they're not really participating in the reaction as much as they are delivering the hydrogen and the hydroxide. So HCl is a solution represented by, God, now he wants to be in the window. An HCl solution is represented by this molecular diagram. In the following diagrams, only the H and OH ions that precipitate or participate in the net ionic equation are shown for clarity. I think there's supposed to be chlorine ions in here as well. Oh, that's gonna disappear. Goodness gracious. Thanks, Moch. Um, so a solution of known concentration of hydroxide is added to the solution of unknown concentration of H plus in the flask, right? Or hydride. At the equivalence point, the moles of hydroxide is equal to the moles of hydride in the original sample, and the titration is complete. And it turns this pink color, which you'll see, if you haven't done it already, you'll see in the video, the lab video. So the equivalence point is usually signaled by an indicator or a dye whose color depends on the acidity of the solution. Usually the concentration of one of the reactant solutions is unknown, the concentration of the other is precisely known. And by carefully measuring the volume of each solution required to reach the equivalence point, concentration of the unknown solution can be determined. So because we know exactly how many hydroxides we're adding to the solution of hydrides, we know that when this changes color, we've matched the hydrides to the hydrogens in a 1-to-1 ratio, so that however many hydroxides we added is also the number of hydrides that are in our unknown solution. And then the pink is just an indicator that helps us do that, which I'm a little bit colorblind, so that was always a hard one for me. I had to have my lab partner tell me when it was, because you really want to get it to the faintest pink color, because that's right when it's at the transition point. And I was not good at that. So sodium hydroxide, so you can be colorblind and be a chemist. Just saying. Sodium hydroxide is added then to our HCl solution when the sodium hydroxide and hydrochloric acid reach the stoichiometric proportions of 1 hydroxide for each hydride. The indicator changes to pink. So phenolphthalein is this pink indicator that we use. I think there are some, it's like, because I'm a little red-green colorblind, so there are other indicators that change at this point, but phenolphthalein is just the one that we use. The classic Gen Chem experiment. So let's say we've got this solution. We're doing a titration of a 20 ml sample of H2SO4, sulfuric acid, unknown concentration. So I always like to write these things out. So if we've got a 20 ml sample, I know me, I will forget to convert it later. We want to be working with liters. So we have 0.020 liters H2SO4, unknown concentration, right? Unknown molarity H2SO4. We know that it requires 22.87 milliliters of 0.158 molar potassium hydroxide to reach the equivalence point. So what is the concentration in moles per liter of the unknown sulfuric acid solution? So we're going to do 0.02287 liters of KOH, and its molarity is 0.158 molar KOH. So because we know that these are reacting in a 1-to-1 ratio, we can just use M1V1 equals M2V2, but there is a slight catch. All right, so we have M1V1 equals M2V2. The molarity of the solution. No, wait, let me think about this. No, so take back what I said. So we can do this still, but we have 0.02287 liters times our 0.158 molar. All right, so this is for KOH, is going to be equal to what molarity, and our V2 is going to be 0.020 liters H2SO4. Actually, let me do it the same way. All right, this is for our H2SO4. Because what we want to know is not what the molarity is after we've added our potassium hydroxide. We want to know what the molarity was before we added our potassium hydroxide. So the reason that this works is if we take liters and we multiply that by molarity, which is moles, over liters, that's going to equal the number of moles of potassium hydroxide that we added, which is equal to the number of moles of H2SO4. And because we're adding sodium hydroxide to this, we have increased the volume, but the number of moles of sulfuric acid stays the same. So that this is, and we're assuming here that this is only removing the first hydrogen from this. So we're getting HSO4 minus. So you can see if we were removing both of the hydrogens, then this wouldn't be 1-to-1, this would be 1-to-2. Working under this assumption though, then we just take, and we can use this M1V1 equals M2V2. And get on my calculator here. So we're going to take 0.02287 times 0.158 divided by 0.020. And so we've got a molarity of 0.181 molar H2SO4. I guess I don't really need this, right? So that's our molarity of our unknown solution. Any questions on that one? These can be a little bit confusing. Not so bad once you figured it out. The other thing that you could do for this is you could write out the reaction equation. So you could write out a reaction equation of H2SO4 plus we use potassium hydroxide goes to H2O plus K2SO4. So yeah, that's where it. If you do this as a net ionic equation, then right, we've got 2H plus 2OH minus. Then we're gonna actually get 2 waters here. Is 2H2O. So you can see that it's a 1-to-1 because then we simplify this. H plus OH minus is H2O. And then what you would do is you would say, okay, well, the number of hydroxides is going to be equal to my molarity times my liters of KOH. Then you could use stoichiometry to say that the number of moles of hydroxide is equal to the number of moles of hydronium or hydride. Hydronium or hydride. But hydride, right? So this is a 1-to-1 ratio. And then you would just say, oh, well, I've got, this is equal to those number of moles. So if I have my number of moles, then I divide by the 0.020 liters to get the concentration of, to get the concentration of the molarity of H2SO4. So there's kind of two ways that you can approach this problem. So to further classify things, of course, because we've got solutions, and I've got acid bases, which happen in solution. We also have strong acids and we have weak acids. Hydrochloric acid is, well, I guess I should just read this. Hydrochloric acid and hydrofluoric acid appear to be similar, but there's an important difference in that HCl is a strong acid, so one that completely ionizes into H plus Cl minus, and HF, which does not completely ionize. So what you actually get is, well, we'll talk about it, I think, in the next couple slides. So when you have HCl, you're going to get complete ionization. It's all going to be H plus and Cl minus. If you have hydrofluoric acid, you'll get some H plus and some F minus, but you're also going to have some of the molecular compound as well. So, right, our strong ions ionize completely, strong acids ionize completely. They're also strong electrolytes. Because they're producing all of these ions, you can actually pass a current through this solution. Just sort of a random note in here. If you see this X in brackets, square brackets, that just means a molar concentration of X. Or if you see like H3O or hydronium here, that's the molar concentration of hydronium. So those brackets are just a shortcut to say this is the concentration in molarity. So pure water won't conduct electricity. We talked about this before. We're talking about ionic compounds. But the presence of ions in an HCl, from an HCl, or from HCl in solution, results in the conduction of electricity. So if you have this circuit here, the electrons can't pass through the pure water to get to the other side. You see there are two electrodes in here. But when we have these ions can actually transport electrons back and forth in the solution. And that lets the current flow through and lights up the light bulb. So these are some strong acids. The monoprotic acids only contain one ionizable proton. An ionizable proton is the one that becomes an H plus in solution. Sulfuric acid, so this is why I was mentioning before, the way I did that equation before is that sulfuric acid is an example of a diprotic acid, an acid that contains two ionizable protons. So if you have a diprotic acid, then you set up your M1V1 equals M2V2. Then you know that the number of hydrogens that you need to neutralize is going to be twice as many. So you can instead say M1V1 is equal to 2 M2V2. Because in that case, it's not just a 1-to-1, it's a 2-to-1. So this would be, right, the number of moles of a diprotic acid. Weak acids do not completely ionize. They contain a few ions. So just in this cartoon over here, you can see that we have a few of these that are still as our hydrofluoric acid, but we also have one fluorine by itself and then one hydronium. Weak acids are also weak electrolytes. Because there are fewer ions in the solution, they don't conduct electricity as well. Oh, and then I should have made a note of this before. So if we have complete ionization, we have a single arrow. because it only goes in the one direction, ionizes completely. If we have a double arrow, what a double arrow actually indicates is an equilibrium. So we have some HF that splits apart into the fluorine and hydronium ion. But then some of those fluorines are going back to the hydroniums, and they're going back to HF and H2O. So it exists in an equilibrium, but the equilibrium is heavier in this direction, and so they want to stay as HF. So we have, again, pure water doesn't conduct electricity, but if we have a weak acid solution, our light glows only dimly, because we have fewer ions present in our electrolyte solution. There's a weak electrolyte. Fewer ions to transport the electrons from the cathode to the anode. Don't worry too much about the cathode and anode terms. There are many weak acids. Most carboxylic acids are weak acids. So we have hydrofluoric acid and then acetic acid. Carboxylic acid is an oxygen with a double bond to a carbon and then a single bond to another oxygen. And so then the carboxylic acid is actually the hydrogen that attaches to this oxygen. Then we use R in organic chemistry to indicate it can be anything else on the end there. So that's what a carboxylic acid looks like, and that's what it's talking about here. So acetic acid and formic acid are both types of carboxylic acid. So acetic acid would be carbon, oxygen, hydrogen, right? And then we have another carbon, and then that's attached to 3 hydrogens. So it'd be your acetic acid, and instead of this CH3 group, called a methyl group, we have just a hydrogen, and this is formic acid. This is acetic acid. Don't worry about knowing the structures here. That's just a little bonus organic chemistry for you. 2 of the weak acids shown here are diprotic. So we have sulfuric acid, and we have carbonic acid. And then we have phosphoric acid, which is triprotic, right? That's the one we talked about before. So sulfuric acid, listed with a strong acid, is a diprotic acid. It's a diprotic acid that's strong in its first ionizable proton, but weak in its second ionizable proton. So H2SO4, strong acid. Once we lose that proton, so this is strong. Once we lose one of those protons to get HSO4 minus, this is now a weak acid to go to SO4 2 minus. That's why it's fairly safe to assume that we were working with the strong acid form earlier, which fully ionizes, and so those are the H plus that we were neutralizing. But the second, going from here to here, is more difficult. Doesn't ionize as easily. Let's take a look at these. A little bit hard to see, but which one of these is a weak acid? Or actually, we're just trying to find one. Which of these is a weak acid? So we're just trying to find the one that's a weak acid. If we start with A, and we ignore the fact that we have hydroiodic acid. But if we look at these are our iodine. And then these are hydroniums, the other ones. We can see that there are no iodines left that have a proton attached to them. So this one must be, because it's fully ionized, this must be strong. If we look over here, the next one, again, we have these NO3 ions that are floating around. And if we look at each of those, these little white spheres are hydrogen. And we don't have any hydrogens that are attached to a nitrate. So again, because it's fully ionized, this is a strong acid. Now, process of elimination, this must be our weak acid if there is one. But if we look here, how many hydroniums do we have? We only have 1, 2, compared to all of these other guys. So this must be our weak acid because we've only partially ionized. Let's see if we can find even the ones that are ionized. Oh, here's an ionized one. There's got to be 2, right? Because we've got 2 hydroniums. I don't think there are 2 in there. There should be another one, I suppose, if it's going to be an accurate cartoon. But so this is again because we only have partial ionization. This is a weak acid. Screen off here. Okay. Let's determine the H plus concentration for each of these solutions. We're just going to assume that each of these is a strong acid because we haven't talked about um, how to calculate the concentrations of H plus hydronium in a weak acid. So if we have, there's an equation for it. I think it's the Henderson-Hasselbalch equation. Anyways, so if we just looking at these, right, we have 0.50 molar HCHO2. It's our formic acid. Our concentration then is going to be. It's so weird that we don't have like a. Honestly, I'm just. There's not a slide in here that talks about how to do that for weak acids. So, anyways, basically what we're looking for here is how many hydrogens do we have? How many ionizable hydrogens do we have? And because there's only one here, this is going to be H plus CHO2 minus. So we see that if we're looking at this as a reaction equation, we have a 1 to 1 ratio. So our concentration of H plus is going to be 0.50 molar. Easy 1 to 1. These other ones are going to be the same, right? So we have hydroiodic acid, and we're going to get H plus I minus. Um, the thing that I'm struggling with right now is that these are all weak acids. Um, but assuming that we have full ionization, we're going to do 1.25 molar H plus. The thing that's going to be tricky, and I'm just going to cross this one out, because we're going to do H3PO4. So we have a triprotic acid. And this is more interesting because we can start with our H3PO4. And that's going to ionize into 3H plus PO4 3 minus. So now how many hydrogens do we have? Well, we have a 1 to 3. So we're going to have 3 times the number of hydrogens present. So we do 0.75 times 3, 2.25 molar H plus. Probably check and make sure that there's not just a slide missing here, and that I'm not missing the fact that I should be teaching you the Henderson-Hasselbalch equation. No, Skill Builder is just that. Oh, I see. Okay. All right, that makes sense. So we're going to be looking at these like this. Because these are weak acids, the most that we can have is 1 to 1, right? But they're weak acids, so we know it's going to be less than that. So this is less than 0.5 molar H plus, and less than 1.25 molar H plus. And even H3PO4 phosphoric acid was on our list of weak acids. It's just more interesting. This is going to be less than 2.25 molar because we're getting not full ionization, we're getting partial ionization. So that's the key for these. Again, the kind of question I would write on the test would be just like this. And right, so if I asked you for this, I say you've got this, how many hydrogens are in there? The answers possible would be something like less than 0.05 molar or 0.50, equal to 0.50 molar, or greater than 0.50 molar. And then since there's only three, I'd probably make up some sort of joke like IDK, don't ask me. That's the kind of question that you would get with these. And the thing that I'm trying to look for there is whether or not you can identify weak acids. Or it could be a strong acid, right? One of these could be a strong acid, and then it would be equal to 0.50 molar. You're never going to get greater than 0.50 molar. Okay. I will, as a note, say that I've gotten a lot more practice now at writing test questions, so I can better tell you what kind of test question that I would write. That's mostly the reason that I didn't before, because I didn't know what I was doing when I was writing test questions. So I was borrowing a lot of test questions from question banks and then modifying them. Anyways, so a strong base. So we talked about strong acids, we talked about weak acids. Now we have strong bases. And again, a strong base, similar to a strong acid, is one that's going to completely dissociate in solution. Unlike diprotic acids, which ionize in two steps, bases containing two OH minus ions dissociate in one step. So you go straight from one to the other. It's not like, so we talk about, right, H2SO4 going to HSO4 minus, going to SO4 2 minus. This happens stepwise, and this step is more difficult. It's not like that with it's not like that with our strong bases. So if you have these um, dihydroxic, right? Because diprotic means two protons. Um, I just made that word up, by the way. Dihydroxic is not a term. But if you have these strong bases that have two hydroxides, those are going to be putting two hydroxides into solution right away. It's not a stepwise process. It's not easier to remove one hydroxide than two hydroxides. So again, our strong bases. We add our sodium hydroxide. We get our sodium ions and our hydroxide ions, right? Fully dissociated. A weak base, on the other hand, is analogous to a weak acid, right? So just like strong bases were like strong acids, weak bases are like weak acids. The most common weak bases produce hydroxide by accepting a proton from water, causing the water to form hydroxide ions. So if we have B, our generic base, not boron, generic base, plus water, then we're going to get B plus our hydride, plus a hydrogen, and then we're going to get OH minus formed as a result. So they're not directly putting hydroxides into solution, but they are indirectly causing water to form hydroxides. So for ammonia, and we make ammonium, we might as well here just say like this is our Bronsted-Lowry, right, accepting a proton, base, Bronsted-Lowry acid, donating a proton, and then our conjugate acid, or conjugate base. It's like ding. Oh, sorry. Yeah. So remember, right? Our acid and our base are our products, and our conjugates are our. Uh, sorry. I said that backwards. Acid and base are our reactants, and our conjugates are our products. Are our products. Um, so this is a weak base because we're mostly going to get just ammonia in solution, but we can also get some of these ammoniums and hydroxides, but fewer. Okay. So there are many weak bases. Organic amines are weak bases. Actually, one second. That's why I heard a ding. Many weak bases. Organic amines are all weak bases. So you have ammonia, and then similar to ammonia, there's pyridine, methylamine, ethylamine, and well, then bicarbonate would be different. But the thing to note is not to memorize these names necessarily, but to look at these structures. Right, so you've got some carbons, some hydrogens, and then most key, you have this nitrogen. So those nitrogens in these carbon structures are going to be the indicator that this is a weak base. Oops. And then you also have bicarbonate. So bicarbonate ion must occur with a positively charged ion such as sodium that serves to balance the charge but does not have any part in the ionization reaction. It is the bicarbonate ion that makes sodium bicarbonate basic. So we have something like, right, you have to have this sodium ion. You can see how each of these reacts with water to form a hydroxide indirectly. Okay, so again, this is a similar thing, but now we have barium hydroxide. So we're going to have barium hydroxide, and again, this doesn't occur stepwise. We're going to have barium 2 plus 2OH minus. So you can see that we have this 0.55 of this. This is a 1 to 2 ratio. So we're going to end up with twice as many hydroxides. So this is going to be 0.110 molar OH minus. But again, weak bases, right? So since it's a weak, oh no, it's a strong base. Sorry. This is a strong base. So it's going to be equal to, right? And I talked about before on the second problem, we have a nitrogen. I believe this is pyridine. So we're going to have our pyridine, C5H5N, plus H2O, because we're making these indirectly, C5H5NH plus OH minus. So once you've written out this reaction equation, you can see that we've got a 1 to 1 ratio. And so we're going to have, because it's a weak base, less than. I made a mess of that. Less than 1.05 molar. Sodium hydroxide. And so this is also, if you write out this reaction to see how it forms hydroxide, if it's forming this indirect hydroxide because it's reacting with water, that's a good indication. And to the best of my knowledge right now, off the top of my head, every time that happens, at least in this class, every time that happens, that's a weak base. These strong bases, let's look at NaOH. Oh, should be a little more careful there. NaOH is just going to be Na plus OH minus. Strong bases have hydroxides formed directly. So then again, this is a strong base, so we're going to have equal to 0.45 molar OH minus. Cool? Water, again, we mentioned this before, but water is amphoteric, and it can act as either an acid or a base. And actually, in pure water, water acts as an acid and a base with itself in a process called self-ionization. So you'll have a distribution of H3O plus and OH minus in your solution. The self-ionization reaction occurs only to a very small extent. It results in equal and small concentrations of hydronium and hydroxide. For pure water, 25 degrees C, the concentration of hydronium is equal to the concentration of OH minus, and each of those has a concentration of 1 times 10 to the negative 7 molar. So that the product then, this is the ion product constant for water, is hydronium times hydroxide to get a total ion concentration of 1 times 10 to the negative 14. All right, we get that because it's 1 times 10 to the 7 times 1 times 10 to the 7, negative 7. So then in a neutral solution, we have an equal concentration of both. So right, our neutral solution, those things are the same. If we have an acidic solution, our concentration of H3O plus is going to be greater than our concentration of OH minus. In a basic solution, we have a greater concentration of OH minus and a lesser concentration of H3O plus. But the important thing to note is in all aqueous solutions, this is true. So if we have more hydroxides, if we have a greater number of hydroxides, that reduces the number of hydroniums, such that the product of those two is always equal to 1 times 10 to the negative 14. And you can see that on this chart. So on the top, this is times 10 to the 0. That times 10 to the 0 then increases all the way up to, well, actually decreases to times 10 to the negative 14. But at 10 to the negative 14, our concentration of OH minus is 10 to the minus 0. So that's the greatest. So if hydroxide is at its greatest concentration, hydronium is at its lowest concentration. And then the opposite is true. If we don't have any hydroxides, then we've got all hydroniums. So they're interdependent. As we increase one, we have to decrease the other. Or as we decrease one, we're increasing the other. So that even, so that as we do the math, it's actually, if we look at each of these, right, this is 10 to the 14, this is 10 to the minus 14, this is 10 to the minus 14, if we're multiplying these together, right, because 10 to the minus 4, 10 to the minus 10, 10 to the minus 14, 10 to the minus 3 times 10 to the minus 11, 10 to the minus 14. So at every single step along this, these always add, well, multiply together to get our H3O plus times OH minus is equal to 1.0 times 10 to the negative 14. Always true. So we can use this then to calculate, if we know the concentration of one, we can find the concentration of the other using exactly that equation, H3O plus times OH minus is equal to 1 times 10 to the minus 14. So we're going to do that here. So if OH minus is 1.5 times 10 to the minus 2, we do 1.5 times 10 to the minus 2 equals 1 times 10 to the minus 14. And so what is the concentration of H3O plus? So just a little bit of algebra. We just take our 1 times 10 to the negative 14 divided by 1.5 times 10 to the negative 2. And our concentration of hydronium then is 6.67, well, 6.7 times 10 to the negative 13. And then if we do our this next one, we have 1.0 times 10 to the minus 7. Again, 1.0 times 10 to the minus 14. And then H3O plus. It's just the same thing. 1 times 10 to the negative 14 divided by 1 times 10 to the negative, oops, wrong button, to the negative 7. My calculator didn't do it in scientific notation, but didn't even really need to do the math on this one. It's 1 times 10 to the negative 7. Just to finish these all out, 8.2 times 10 to the negative 10 is equal to 1 times 10 to the negative 14. So you do 1e negative 14 divided by 8.2 e negative 10, right? Because the e is the times 10 to the negative button. That's 1, 2, 3, 4, 5. 1.2 times 10 to the negative 5. So you can see that when you add this coefficient here, when it gets to be something other than a whole number, or other than 1, it's a little bit confusing how things add or things multiply together to get to times 10 to the negative 14. It's not so straightforward. Fortunately, so that we can avoid writing all these times 10 to the negative 5s, we have an easier way of denoting acidity, and that's pH or pOH. So if the pH is less than 7, we have an acidic solution. If the pH is greater than 7, we have a basic solution. And if pH is equal to 7, we have a neutral solution. But what is pH? pH is the negative log of the concentration. So because we're using the negative log, if you take your calculator right now and just do negative log of 1 times 10 to the negative 4, you will get 4. So that's this first one here. Just use this more. 1 times 10 to the negative 4, that's 4. But when we use a log scale, going from 4 to 3 isn't just a decrease of 1, or actually it's an increase. Because we have negative exponents, we're raising to the negative power of 10. So actually the concentration is getting bigger as our exponent gets smaller. We don't just have 1 more, we have 10 more. So we go from 1 hydronium to 10, and if we go from 2, that's times another 10, so that's 100. Because this is times 10 to the negative 2, lost my pointer, times 10 to the minus 2, so it's 1 over 10 times 1 over 10. So as this pH gets smaller, our concentration gets bigger every time by a factor of 10. Okay. Logarithms is one of those things that I've used for a very long time. And so explaining logarithms is difficult. I will link, actually I'll link it right here for everybody who's going to watch it on Zoom or those of you who are in the chat. Khan Academy, it's a great video explaining what logarithms are. For our purposes, we only use base 10. So in the Khan Academy video, they use multiple different bases. For example, let's think about what our exponents are. So if we have 2, let's just do, we'll do 2. So this is the example from the Khan Academy video, actually. Because he can explain it better than I can. So 2 to the 4th power. What does that mean? That means that we have 2 times 2 times 2 times 2, which is equal to 16. So when we raise something to a power, we're multiplying by itself multiple times, right? So if you have 10 to the 4, that equals 10 times 10 times 10 times 10, which equals something like 10,000. So what we're doing with a logarithm is the logarithm takes this and it asks the question, 10 raised to the what will equal 1,000. And so, if we know something about exponents, we know that that x equals 3. So the logarithm then, if we were to write this as the log base 10 of 1,000 equals x. Here x equals 3, right? So the question that we're asking is, what power do I have to raise 10 to get 1,000? And in this case, log base 10 of 1,000 is equal to 3. So for this, we're always using base 10. So when you see log as log on your calculator, that's log base 10. Log as ln, that's base e. E is Euler's number, and it's like 2.71. It's called the natural log. We're just using log 10. So when we say that we're taking the negative log, let's go back to this previous page. So let's just take 10 to the minus 4, right? So we're going to do the negative log base 10 of 1 times 10 to the negative 4. And so what we're asking is, what exponent do we have to raise 10 to get 4 times 10 to the negative 4? But then we want the negative of that because we want to work with positive numbers. So the answer in this case is simple because we already have the exponent here and we're already working in the same base. So the answer is just negative 4, but we're multiplying by a negative. So our answer is going to be positive 4. I guess I should do this without the negative as well. So if we did log base 10 of 1 times 10, I don't know, to the negative, let's do 40. Why not? So what is the answer here? If we have 1 times 10 to the negative 40, what would the answer of this be? It would be negative 40. And so because we want to work with positive numbers, that's why we use the negative log here. So that's for pH. The same goes for pOH though. And actually, let me swap back here a few slides. Okay, yeah, with this scale, right? So the negative log of 10 to the negative 1 is going to be 1. The negative log of 10 to the minus 2 is going to be 2. Negative log of 10 to the minus 3 is going to be 3. It does get a little bit weirder. This only works super easy like this when it's 1 times 10 to the negative. If we get something like 3.5 times 10 to the negative 4 as our, well, I could just write it like this, right? Because this means H3O plus. That you're going to want to type into your calculator. But what you're going to type into your calculator is just going to be log. It's not going to say base 10. Your calculator might have an option to change the base. But if you just use the log, that's going to be your log. And you just type in 3.5 times 10 to the negative 4. So we're going to do log 3.5 e negative 4. And our answer is going to be, negative log, because we want the negative log as the pH. We're going to get 7.86. Or I guess we'd use two significant figures here, but this would be our pH. So you can see things do get a little bit, it's not super, oh wait, I'm sorry, I did the natural log. Um, 3.5 e negative 4. Okay. It's like that doesn't seem right. And it wasn't right. So it's 3 point, we'll do two significant figures. So 3.6 would be our pH. Okay, so if you're not super comfortable with that, if it's still not making sense how logs work, or logarithms, again, check out that Khan Academy video. I think there's a whole series, or there's at least a few videos. The one I linked is the intro video, which lays it out here, sort of like I did here. But again, for pH, we're using log base 10. So let's convert these numbers then from this molar concentration to the pH. So we're going to get, again, right, the pH is the negative log of the molar hydronium concentration. We're going to do 9.5 times 10 to the negative 9. If you have the TI-36X Pro, uh, you have to press the log button twice to get the log base 10. So please don't make that mistake. On an exam, that would be unfortunate. So 9.5 e to the negative 9, and I'm doing the negative log. So it should be, our pH is 8.0. So we only have two decimal places. And again, this is just the same thing, negative log of 6.1 times 10 to the negative 3. 6.1 e to the negative 3. And we're going to get 2.21 as our pH. I'm sorry, 2.2. So actually, let me try and make this full screen. I can just show you what this looks like on my calculator. A webcam. I don't know if this will work. It's like, that's not a face. Oh, I actually can't turn off my... The background, the software I use to do the background replacement is freaking out, so I can't actually show you this. Bummer. Okay. This is pretty much what it looks like in the calculator, right? It should say log as log. So if we have the pH is the reverse process of this. So let's take a look at this again. We have the negative log base 10 of, right, a concentration. Let's just put in 1 times 10 to the negative 5. Okay, right? So this equals 5. But what if you have a pH? Well, if you have the pH and you don't have the, again, I just always write sideways like this. If you have the pH and you want to go back to your concentration, that's almost easier, because you're just going to do 1 times 10 raised to the negative whatever your pH is. So in this case, it's 5. And this would be your concentration.
You know that we can't see your iPad screen?
Oh, yep. I mean, I did know, but I didn't know. Thank you for reminding me. Right, so the negative log, right? So we have the negative log base 10 of some concentration that equals 5. If we want to go back from the pH to the concentration, then we just raise 10, whoops, we just raise 10 to the negative pH. So here 1 times 10 to the negative 5. But you can also get something like, let's say you have 6.43. It's the same thing, but you'll type it into your calculator as 1 times 10 raised to the negative 6.43. And what you'll want to report as your answer is the result of that. So you just do 10 to the negative 6.43. Just double check. Can I? Here we go. Give me the scientific numbers, Mr. Calculator. So this would be 3.71 times 10 to the negative, negative 7. So this is the concentration as you would report it.
Wouldn't it be 3.72?
Oh, yeah. Okay. That was 1 hour, but we just got 7 slides left. So we're just going to finish it out real quick. So let's calculate the concentration of an H3O plus concentration for a solution with a pH of 8.37. So if our pH is 8.37, we're just going to say 10 raised to the negative 8.37. 8.37. Oh, that's right. That's why you can't do that. Okay, so you cannot do, or at least on my calculator, it won't let me do 1E 8.37. This is again the TI-36X Pro. Instead, there is a small button that looks like it has an E with a square and a 10 with a square. If you press that button twice, that will give you a readout that looks like 10, and then there will be a box here that blinks, and that's where you're going to be filling in this negative 8.37. So we're going to get 4.27 times 10 to the negative 9. And then our unit would be H3O plus. So you write this units as either H3O plus like this in brackets, or as molar H3O plus. Cool. Now the relationship between POH, so POH is the negative log of the OH concentration, but one of the cool things about logarithms is if we have the log, so we have the negative, back up a step. If we have the concentration of H3O plus times the concentration of OH minus is equal to 1 times 10 to the negative 14, we can take the negative log of both sides of this. So we'll do the negative log of this, and we'll do the negative log of this. And when we have two things that are being multiplied together inside of a logarithm, we can actually break those apart. And so we can do this, is we can have the negative log of H3O plus the negative log of OH minus concentration. I forgot the brackets there, but of the concentrations of each of those is equal to the negative log of 1 times 10 to the minus 14. And what that does for us is, now that we know the negative log of H3O plus is just pH, plus the negative log of OH is POH, and then the negative log of 1 times 10 to the negative 14 is just 14. So pH plus POH always equals 14. So if you have POH, you can calculate pH. If you have pH, you can calculate POH, because they're always equal to 14. And then from there, you can get the concentration in molarity. And then if you have the volume, you can calculate the number of moles. Let's calculate the OH concentration for a solution with a POH of 4.25. Okay, so we have POH, or 4.25 POH. So we're just going to do, it's exactly the same as hydronium, right, or H plus concentration, except now we're talking about hydroxides. So we're just going to raise this to negative 4.25. So negative 4.25, and that's 5.62 times 10 to the negative 5 concentration of OH. Oh, wait, what? Really? We're not going to? Okay. So if we wanted to then say, okay, we know the POH, but what is the pH? We could say pH plus POH is equal to 14. We know our POH is 4.25 equal 14 pH. So all we have to do is subtract 4.25 from 14 so that our pH is equal to, type it into my calculator so I don't make a mistake, 9.5. And then from there, we could do 10 raised to the negative 9.5, and that would give us our, I'm just going to use a number because I'm not going to do the math, times 10. I
Isn't
guess
it 9.75?
Oh, it's 2.5. I'll type it in my calculator so I don't make a mistake, and then I make a mistake. Because you're right. I typed 4.5 in. pH equals 9.75. 75. I might as well just do it. Raised to the negative 9.75 would be 1.78 times 10 to the negative 10. And that would be our concentration of H+. So if you have one, you can get the other. Really pretty easily. So the last thing we're talking about, just very briefly, is buffers. Buffers contain significant amounts of both weak acid and its conjugate base. So the weak acid neutralizes any added base, and the conjugate base neutralizes any added acid. So if you're adding acid or base to a buffered solution, the pH isn't going to change very much until you use up your acid or your conjugate base. Human blood is a buffer. So in a healthy individual, in a living individual, your blood pH is between 7.36 and 7.4. And if your blood pH were to drop below 7.0 or rise above 7.8, death would result. Because a lot of the functions in your body rely on that pH to take place and to continue living. Acetic acid and sodium acetate buffer system looks like this. So we have, when we add a base, we're reacting the base with the acetic acid to form our conjugate base in water. But if we add acid, then that can react with any conjugate base that's around to form acetic acid and a salt, here sodium chloride. Because we have in equilibrium both the acid and the base. We're going to look at more of this. Yeah, so the acid in a buffer consumes any added base, and the base consumes any added acid. So we've got, these are the acid, and this is the base. We have both of these present, and so if we add one, the other will pick it up. So we add base, right? These get picked up by the acid. If we add acid, then those are picked up by the base. All right, so if we look at these, which of the following is a buffer solution? So we need an acid and we need a conjugate base, or we need a base and a conjugate acid. Here it looks like all of our acids are listed on the left, so that's convenient. So HSO4 and H2SO3, both of these are just acids. So we've got two different types of acid. This is not a buffer solution. Here we have hydrofluoric acid and sodium fluoride. So we have a weak acid and we have its conjugate base. So that is a buffer solution. Here we have hydrochloric acid and sodium chloride, but probably have to go back and look this up, but hydrochloric acid is a strong acid. We need a weak acid. So we need a weak acid, and we need We need a weak acid and a conjugate base in order to have a buffer system. Sodium chloride isn't even an acid. And then we have a base, but this is not then a buffer solution because we don't have a weak acid. It might be the last. That was the last
Go
slide.
over A again. Why was that not?
Oh, this is not because we have two different types of acid.
Okay.
Yeah. You could, in theory, have a buffer system of HSO4 minus and SO4 2 minus because the second ionization is a weak acid. So that's why you have to have the weak acid, which, H2SO4 is a strong acid. I think H2SO3, I believe, was a weak acid. Have to check. But you also need a conjugate base. Yeah. Are there any other questions about this? No? Cool. All right. Um, yeah, thanks for coming. That was chapter 14. Tomorrow we'll do chapter 15. Again, there's a test on Friday. Oh, I am planning on taking. I still need to find out when grades are due. But I'm planning at this point, at least, on taking late work up until Sunday. Um, After that, I'll update with an announcement if that changes. Um, Otherwise, Sunday's the last date. There's also going to be a test on Friday. Again, I'm going to do noon. Yeah, I'm going to do noon from noon on Friday to 6 p.m. again on Saturday. So the same as the last two exams. Again, shooting for around 50 questions. Go back at the previous two exams, look at those, and look for questions that have been repeated. Because those are ones that people have struggled with a lot, and even though they've been repeated, have been missed. So go back, look through those. Those will also give you a good idea of the kind of questions that I'm going to write, if you can kind of suss out how that works. Anyways, I think that's all I have to say. So thank you for coming. Thank you for watching, and I will see you again tomorrow.